Well, welcome to this tutorial. Today we're going to be looking at what is called a state machine, or I prefer to call it milli controlled code. Now basically what this is about is how to have multiple items, inputs and outputs, being controlled at the same time. Now, one of the problems with the Arduino is one of its benefits. The joy of the Arduino: you can take it out of the box, you can load up the blink sketch, and before we know it we've got a wonderful blinking LED, and then of course we add some more external LEDs, and before we know it we've got a little light pattern displaying. But one of the great problems is that even in some of those most basic sketches we actually start to teach ourselves some bad habits. So what I'm going to do is just switch to my other screen. Where are we? There we go. So this is the traditional blink sketch, and obviously it puts the LED on for 1 second, turns it off for 1 second. The problem is with a Arduino, when that delay takes place, the entire Arduino basically stops. It's doing nothing. Now if you're just turning an LED on and off, that is not a problem, but as we'll see, as we start to try and do other things, this causes an issue. Now what I'm going to do is I've just loaded up a blank sketch, and the first thing that I want us to think about is just how fast an Arduino is. Now you look at that little board and you think, you know, it's not that powerful, it's not a computer. It actually has a speed of 16 megahertz. What does that mean? Well, in its most basic form, if we look at this loop here, the void loop, if we didn't put any code in here, realistically that means at 16 megahertz this loop is going to run 16 million times per second. Just want you to think about that. That loop is going to run 16 million times per second. That means that even though our little Arduino is not powerful by computer standards, you know, these days a modern computer, what it's running at 3,500 megahertz, something like that, with multi-cores, but still 16 million times per second is very, very quick. And what we're going to look at today is not only how to write our code so that we don't block things, but also have a think about some of the very simple things that slow our code down. Now to start with, we're going to look at what I call the blocked blink example. So this is the code. It's very, very simple. It's on the Digital Town website. There's a link below the video to show you where to get the code. So this is a very simple sketch. It's got a red LED, a button that is controlling that LED. It's got a byte that's storing a simple 0 or 1, which is the flash state. I begin the serial. I just print out the title of the sketch. We've got the pin mode for the two items. Obviously the LED, the button is an input, the LED is an output. Now what happens in the sketch is if the flash state is smaller than 1, the LED goes high, just like in the blink sketch, except instead of delaying for 1 second I'm delaying for 5 seconds, and I'll explain why. Then we're going to turn the LED off and we're going to delay for 5 seconds. Now before we go any further in the code, I've put some speeds in here to give you an idea of how fast something happens on an Arduino. So when you send your little command digital write, it does some stuff in the background. it's using up what we would call clock cycles. Certain things are having to happen. Basically, when a clock cycle happens, something happens in the processor. It takes an instruction and it does something. So we're going to say that to make the pin go high, I've taken a guess and said, I used to write some assembler code years ago, and I'm going to say it's going to take 16 items to get that pin to go high. It's probably less, but I'm being a pessimist. But even if it took 16 clock cycles to get that pin to go high, that has taken 1/1,000,000th of a second. That is fast. So it's taken 1/1,000,000th of a second to turn the LED on. And then our super fast Arduino, we use the code for delay, and it literally locks itself up for 5 seconds. For 5 seconds, it is literally going to go round and round in a loop, doing nothing. Now, when I say it goes in a loop, it's not going round this loop. Okay, what it's done is it's done this instruction, then as it gets to the delay, basically it sits here twiddling its thumbs, going round and round in circles on this line. When it gets to the end of the 5 seconds, it takes about 1/1,000,000th of a second to turn the LED off, and then it sits there for another 5 seconds twiddling its thumbs, doing nothing. Now, what I've done lower down is I've got a digital read, so it's going to read the button, and if the LED is flashing, it's going to stop it flashing, and if it's not flashing, it'll start it flashing. Now, what I'm going to do is just show you this in action. First of all, I'll just show you the test rig. Right, this is the test rig we're going to be using for these sketches. If we zoom in, we've got a couple of buttons. As you can see, they've got a resistor, a pull down resistor going down to earth, and then we've got 2 red LEDs, one of which happens to be blinking at the moment. We've got in the corner an orange LED, a green LED, and we'll be using the built-in board LED, which is down here somewhere. So that's the hardware that we're using. Don't worry about this green wire at the end of the board. That's actually just holding the Uno, stopping it moving around on the breadboard. So that's the hardware setup. So now you've seen the appalling video from my phone of the hardware setup. Let's have a look at this sketch running. Now, in our blocking code example that this Uno is running at the moment, I've got an LED that is coming on for, I think it's 5 seconds, going off for 5 seconds. If I want to control it, which is with this button here, I've got to press it at just the right time to stop the cycle. No, can't do it. I'll be honest, in practice I spent ages doing this. You've basically got to hold the button down and hope you get it. No, still haven't got it. As you can see, it's not reading the button input because of all of those delays. It's constantly blocking it's not reading from the button for most of the time. That's the problem with blocking code. So you've seen the video, so let's go back to the code and look at the problem again. So we've got 1/1,000,000th of a second to do this, 5 seconds of hanging around, 1/1,000,000th of a second, 5 seconds of hanging around, and bizarrely it's going to take 1/1,000,000th of a second to read the button and change these states. The problem is, if I press the button during that 5 seconds, or during that 5 seconds, even if I press the button right at the beginning here and hold the button down for 8 seconds, still the code has not got to the point where it reads the button. Now I could cheat on this and just hold the button down. Yes, I could bodge this particular sketch, but I'm a model railway fan. A lot of my stuff is to do with model railways, and if these were going to be some crossing lights for a level crossing, I might want a sensor to pick up as the train came along, turn my flashing lights on, and then when it went past the exit sensor, turn the lights off. Now, if you can imagine, it might pick up the entrance as it came in and start the LEDs flashing, but of course if the train passes the stop sensor during this period, then it's never going to turn the lights off. It's just going to leave them on. And this is the problem with blocking code. Now, to try and explain a state machine, I'm going to go back to my really old programming days. So let's load up this next sketch. So, years and years ago, I used to program the old Atari computers, and we used to write in assembler in those days. My goodness, it was sad times, or good times. But let's have a look at basically how a computer works and look at it in an Arduino sketch system. Obviously this sketch is never going to run, but if we can imagine in our setup, the computer would read from its hard drive, or sometimes in those days it was a floppy disk or even a tape drive. It'd get the operating system up and running, it would load the drivers, connect the devices, very similar to your modern PC. That's what it did during, if you like, the setup phase. Then we got into what was called the loop, and in those days I used to have to program all of this manually. So if you can imagine, on your computer today, you want to be able to press the keyboard, move your mouse, you want to be able to click a button. The system is also receiving time updates from its internal clock, and it may be receiving data over the internet or a network or various things. So if you like, those are the things that you want to be able to have as inputs. At the same time, we've got outputs. We've got calculations and processing going on. You know, if you've got a spreadsheet or your word processor, obviously you want the screen to update as you're doing this stuff, so screen updates, even if you haven't got a program running. You know, bottom right, I've got a clock. I want the clock to update. I might be writing to the hard drive, I might be transmitting data. And I want all of this to be going on. And if you can imagine, I don't want the situation where when I'm trying to update the screen, the rest of the system, all the inputs lock up, and at the same time when I press the keyboard I don't want other stuff locking up. I want these things to happen simultaneously, or at least have the perception of being simultaneous. Now I know modern computers have multiple cores, and even if you're using an ESP32 processor, you've got dual cores, but I want us to think for now as if we've got a single core. Now obviously it can't do everything at once, so it's got to do all of these things and check all of these things. So the way we used to write our code was to make it run through this loop as quickly as possible and not get it stuck anywhere. And this is where your problem with your delay came in, because if we imagine, if we put a delay in here, let's just type in delay 5000. If we now think about our keyboard, we've pressed a button on the keyboard. It's now going to hang around for 5 seconds. We're twiddling our mouse, we're pressing our buttons, we're waiting, we've got a clock, nothing's happening because the processor is locked up for 5 seconds. And this is very similar to what happens with our Arduino, that instead of having these keyboards we would be using maybe a button, maybe it's an input sensor, a reading that we're taking off a distance sensor. Those would be our inputs. You know, we may be receiving data over serial, and then we've got our outputs, which could be a screen. We're processing stuff, we're writing data not to a hard drive, maybe to an SD card or an EEPROM. We're transmitting data. It's the same system, and what we've got to do is try and do all of this without blocking. So let's have a look at some of the things that maybe block our code and write some code that works well. Now, going back to our test setup, here we have what I would call a typical model railway type effects. So we've got a couple of LEDs that are running as crossing lights. We've got an orange LED which is doing what I would call some fire flicker code. I've got a green LED which is just flashing on and off once a second. Basically, it's doing blink. I've just put it in there. Who knows what it would be used for? Pedestrian crossing maybe in the UK if you had the right colour LED. And then on the board, I'm also flashing the board LED. I think it's once every half second, just to have something else running on. Obviously, there could be more effects running, but this is enough for now. Now, before, if you remember, when I pressed the button, because of the way the code was using endless delays, none of the button presses were recognized. So on this first one, this end button here, I'm going to press this one and you'll see that this stops the onboard LED. There we go. So that stopped it. As you can see, nothing else is impacted whatsoever. If I press it again, there we go, it's flashing. Now, that one, obviously, if I had pressed the button at the point that the LED was on, it would have stayed on. Now, if we're thinking about crossing lights, when I stop the crossing lights, I want both lights to go off. So in this case, when I press the button, oops, hang on. There we go. That's right, sorry, my connections are all a bit loose here. Trouble with breadboards. But there we go, turn it on. Turn it off. Turn it on. Turn it off. So, although I'm using a button here, in reality on a model railway you may use a button for that, but you would probably use some kind of sensor that's sensing that the train is coming along. You then want it to turn those lights on, and then once either a time period has gone by or the train passes another sensor, it turns the LEDs off. So now you've seen the example of a finished state machine, let's have a look at how the code is actually written. Now, what I did was a number of different effects, and I've broken them down into sections to try and make this as simple as possible to understand. So, in my typical system, there's a bit of a header here explaining how it all works. I've listed the pins that I'm using. I tend to do that on every project I work on. I just list out the pins in a comment section at the top, just so that I know what is being used for what. It's a good habit to get into. Now, again, I've defined all my pins, said what I'm doing with them. I've got one item here, an unsigned long called current millis, that you'll see in a bit. And at the beginning, we're just going to deal with the green LED. Now, if you remember, the green LED is flashing on and off once a second. It's doing blink. So let's go down through all of this code, look at the setup. Obviously, we're just doing the pin mode for all these things. I've done a serial print just to say what code is running. I find that useful in that if I've been updating code a lot, it just allows me to plug something in. If I'm taking something off the railway that's been there for a year or so, I can see what version of the code was actually on the board. It just helps me. So the first thing in the loop that I do is I get the current time in milliseconds. Now, this isn't the time of the day as in real time. This is the number of milliseconds since the board was turned on, basically. So if your board's been on for 1 second, 1,000 milliseconds have gone by. And we're going to be using this timing throughout this program. Now, On this system, I've actually just called this once at the very beginning of the loop, and then it's used in each of the functions. It just saves a fraction and, you know, milliseconds in calling it later, but it just makes my code a little bit cleaner for me. So the first thing we're going to look at is how the green light is working. So if we go up to the green light, here we go. I've got a function called green light, and in there I'm declaring a separate integer, which is the green delay, 1000 equals 1 second. And using millis, this is a way that you use millis, so it's saying if the current time minus the green timer is greater or equal to the delay, then do something. So, and then of course it resets the green timer to the current millis so that it'll go round and do this again. Now if the state of the LED is greater than 0, so when we look at the green LED, there's not just a timer, there's a state. Now if you think of your normal blink code, let's get the example. Where are we? Examples, basics, blink. So if we look at the basic blink code, we never actually need to store whether the LED is on or off, because it's on and then we turn it off. That's great if it's the only thing happening, but if you can imagine, in this bit of code, as you'll see later, as we run through this loop, it's going to go into this function, this function, this function, this function, this function. It's going to be messing around with everything. So when we've turned the LED on or off, we need to remember whether we turned it on and off. So this is stored in this variable called green state. So if the variable is greater than 0, so at that point the LED is on, it sets green state to 0, turns it off, else it sets it to 1 and turns it on, and then it does the digital write to change the state of this LED. Now to give you an idea of how fast this is running, that if statement is probably going to take about 0.3 of a millisecond. That's how quick it's going to run. If it's obviously got to do anything to do with this, it might take another 0.3 of a millisecond. That's probably being pessimistic, but basically even when it's working on this sketch at its hardest, it's not even going to take a millisecond to run through that bit of code, because there's nothing in there that's blocking anything. Now that means when it goes into the next function, even if it's done a whole load of work in here, less than a millisecond of time has gone by. Now it's quite hard to get your head around this when you're new to programming, but just to give you an idea, if we go into the reference for the Arduino, you know, often you'll see delay and we're using millis. But you see we've got delay, we've also got delay microseconds, and we can use millis as a timer. We can also use micros. My goodness, if you needed really exact timing, you can actually time things to 1/1,000,000th of a second. Now obviously we don't, in the model railway world, I really don't need that, but it just gives you an idea. Even when it's timing to 1/1,000,000th of a second, the Arduino still has 16 other clock cycles per second per change in state. So you might think that, if you like, that timer is going up very quickly once every 1/1,000,000th of a second, but for the other 15 clock cycles your Arduino is sat there bored, twiddling its thumbs. That's how quick these boards can actually be. Now if we get back to our code, so the green light, as we've seen, is a very simple example. It's just, and again, this is why you start to call these things state machines, because it's checking the state of something every period of time, and then if it needs to, it's changing the state. So with the LED, it's changing it either on or off. So that's a very simple one that I did at the beginning, just to give you some very, very basic code on how this thing works. Now, if we go down to the bottom, the next thing is the fire flicker. Now, with a fire flicker, if you can imagine, I don't want it just blinking on and off. Fires don't blink on and off. They sort of have random intensities. Those intensities change at random intervals. So in this function, we're going to use a couple of random calls. So here is the fire flicker, and this time we've got fire delay. Now, fire delay is not held within the fire flicker function. It's actually up here. Now, the reason for that is that the fire flicker delay changes with each version of this, so I need to store that outside of the function, otherwise it's going to get destroyed. So if the timing is correct, exactly the same, we've got a different timer. Each item has its own timer, so name your time as well. So we've got the fire timer. Again, if this if statement is good, reset the timing and then reset the delay. Now I'm using a random value between 30 milliseconds and 200 milliseconds, so that's 0.03 and 0.2 of a second, and it can, basically choose any time between there. And then what it's doing is it's doing an analog write to the orange LED, and it's picking a random value between 0 and 255, and this is basically using PWM to change the brightness of the LED. So we're getting a random delay and a random brightness, and all of this code, again, because we haven't got any delays or anything in there, this code in total I would think is going to take about 0.03 of a microsecond, if that. This thing is running ridiculously fast. So although it looks like the LED when you're watching it on the board is working hard, the code is absolutely flying by. Now, I then got our first controlled item, which is the board LED flash. I'm using buttons, but obviously a lot of things, this could be a sensor that we were using. It might be reading from different sensors. Those are going to be found when we get to the button presses. So first of all, we go to the board LED flash. Again, all this code is on the Digital Town website, so you can go through it in your own time. So we have got the board delay. I was wrong. I'm flashing that thing on every 0.1 of a second. Who knew? It's flashing really quick. Again, from an Arduino's point of view, that might sound like it's working hard. My Arduino is still sat here. It's got enough time on its hands to go and make a cup of tea, do what it wants. So later on we'll see if the built-in button state is a certain value, this item will flash. If not, it won't flash. So what we've got here is exactly the same code as we saw in the green LED, but instead of flashing it on and off once a second, now it's every 0.1 of a second. So that code is exactly the same. The only thing I've done is surrounded it by an if statement, and that if statement is to do with have I pressed the button, and we'll get to those buttons later. So if the button state is 0, it'll keep working. If I've pressed the button and the state goes to 1, it'll stop. And if we go down to our button state code, so button press is at the bottom of my loop. It really doesn't matter which order these in. If you've got something that's absolutely timing critical, I would tend to put it at the beginning of the loop as close to when I read the milliseconds as possible, but it really isn't going to make any difference in these particular sketches. So what I'm just looking for now is the button press. Now there is a debounce thing in here. A debounce is if I press the button, because it only takes less than a microsecond, a millionth of a second to read the value of the button, if I try to press the button, I can't press it and get my finger off the button inside a microsecond. I'm too slow for that. If you can imagine, if you were typing on your keyboard and there was no debounce on your keyboard, the first letter you pressed, if you held it down for even sort of 0.1 of a second, you're going to finish up with sort of 500,000 characters going across your screen. So we have to put a delay in there just to give us enough time to get our finger off the button. So the first thing it does with my buttons is it just checks, have I given it enough time since the button was last pressed? Otherwise I'll be turning it on and off endlessly. Now I've got in my code up here, when we look at the buttons, we've got two buttons. I've got the built-in LED timer. You're starting to see now, aren't you? A state machine consists of timers and a state, the button state. Hence this title, State Machine. So if we're looking at the built-in button, we're checking if the debounce has passed. If you were using a sensor, you might do a similar thing. You might have to sort of put a delay in, otherwise it would be constantly triggering something. So if you can imagine, if your train comes to a sensor, you might think, okay, I don't want it to trigger that again for another period of time. Or you might use something that only sets the sensor, the state in one direction, and you use another sensor to trigger the state in the opposite direction. So if the debounce time has gone by, we're just going to check if this button is now currently being pressed. If it is being currently pressed, then what we're going to do is we're going to check what was the button state. If the button state was 1 greater than 0, we're going to set it to 0, else we're going to set it to 1. We're going to change the button state, which if we go back to our where are we, board LED, before it does anything, it just checks, is the button state set in a way that I want to be flashing this LED on and off. If you remember as well, when I did the video, when I pressed the button, if I had pressed the button when the LED had been on, because this doesn't do anything to turn it off, it will just stay on until I press the button and it starts flashing again. I've done that deliberately just to make you think about it. Okay, going down to the bottom. Now we're going to get to the complicated one. Now we're going to look at two red lights. I've done them in a style of an American railroad crossing. Ours are done slightly differently in the UK, but I've done it specifically for that reason. Now, when we do the red lights, there is a delay that I'm using. Now, when we talk about a delay here, I'm talking about the time between the alteration of the brightness of the LED. In this code, there is no delay, but this is just telling my system how long it should wait until it makes an update. So the first thing, if you remember, I've got a button that controls this system. So is that button state set as greater than 0. If it's greater than 0, it's going to stop the lights flashing. It sets the fade value to 0, that's the brightness of the LED, and then it does an analog write to both LEDs and it turns them both off. I've put them at the beginning just to make it easier, otherwise they get lost right at the bottom and it gets a little bit more difficult to follow the code. So if the LEDs, if we're turning this system off, it immediately turns off both LEDs. Otherwise we want things flashing, and guess what? We use a timer that is checking the fade delay. Now if you remember, we've got, at the moment I've got 1 in here, which is actually 1 millisecond rather than 10 milliseconds. I shortened it because I found 10 milliseconds it didn't work, it didn't look quite right. Again, you can just change that value to change the flashing speed of your LEDs. Now we've got our fade timer, and this time with the LED we've got to have more states saved. So if you can imagine, we've got on and off, but when we look at our red LEDs, here we go, here's the things that we're storing data in. We've got the current fade LED, that is which of the LEDs is currently being worked on, the left LED or the right LED. Then we've got the current value that's being passed to that LED, and then I've got a state called fade direction. You'll notice most people tend to put integers in here. I'm using bytes. This code is very, very small. It's not exactly going to take up much space on the Arduino. What does it take in here? 10%, you know, 3,000 bytes. It's nothing. But if you were writing something very big, storing values takes up space. A byte takes up half the space that an integer takes up on an Arduino Uno. So I just like to save the space because it's only storing values less 255 or 0, which is enough to fit in a byte. That's why they're bytes, not integers. If you put integers in there, it wouldn't affect the code. But I tried to do it in as space-saving a way as possible to try and keep in good habits. So fade direction is another state that we're saving, and this is saving whether we are increasing the brightness of the LED or we're decreasing the brightness of the LED. And then finally we've got the fade timer, which is basically saying let this code go round and round in loops, and every 0.1 of a every sort of 1 millisecond make an alteration to the lighting setup. So here we go, the red lights. We've checked the button state, we're not turning it off, we're now turning it on. So 0.1 of a second has gone by. I do need to change that. 1 millisecond's gone by. We've reset the fade timer. You'll notice I did a serial print in here. This was just while I was testing. It's commented out, and this is something that you just need to think about. A serial print statement, I did some tests earlier, just to print an integer value takes about 4.5 milliseconds. Now this is just to do with the way that the data is passed to the serial port, and obviously there's buffers and there's bits going on in the background that we don't need to worry about. But what we do need to think about is the fact that it takes 4.5 milliseconds to do that right. Now that's just for a small number. If you put Digital Town, for instance, if you sent Digital Town through, that's going to take 9 milliseconds. Now when we start to think about the fact that our code here is running in microseconds, 9 milliseconds suddenly becomes a very, very big thing. Now it wouldn't make too much of a difference if we've just left the 1 in, but could you imagine if you're writing a big piece of software and you've left these serial prints in everywhere? And I did this on a piece of code. I was writing a touchscreen controller and the screen was so laggy it was unusable, and there I was sort of cursing the screen, and it turned out that in the background I'd got a load of serial prints running, checking what I was going to display on the screen, and they were causing ridiculous speed decreases on the system. So when you're writing code, by all means put your serial prints in to check what's going on, but when you've finished and you're loading it up into your finished project, make sure that you comment them all out. Otherwise you are going to have some problems with lag within the system, because basically that is causing my code to be blocked for 4.6 milliseconds. Doesn't sound long to us, but for an Arduino that is an eternity. So getting back to our code, fade direction. So if the fade direction is smaller than 1, I increase the value of the fade. If it gets to 255, which is the maximum value, it changes the fade direction. So if you like, it's increasing in brightness until it gets to its maximum value. Then we change the state of the direction. So next time it reads this, it will decrease it. So if now that value had been 1, instead of increasing the value here, we start decreasing the value. So the fade is getting, the LED is going to get duller. If I obviously get to a value of 0, it changes the fade direction, and we go back and we make it brighter. Then we've got 2 different LEDs. Obviously I've got a left and a right. Which LED am I working on? When it gets to 0, not only does it then change the direction of the fade, so it's now, our fade has gone until the LED has gone out, then instead of relighting that LED, it swaps our current LED to the other LED. So the first LED has, if you like, our left hand crossing light has gone out, and now we turn our right hand light on. It increases in value and decreases in value, and once again when the value drops to 0, not only do we change the fade direction, but we change which LED it is actually doing. Now if you're doing a railroad crossing, just so you know, if you were doing this, there could be a number of LEDs in the system, so I'm only using 2, but when we actually use that state, which current LED are we doing? If it's greater than 0, we're going to do LED 1 is going to get the fade value. If it's smaller than 0, LED 2 is going to get the fade value. If you were doing a crossing where you wanted lights on both sides of the road, which would be obvious, you would just put more LEDs in here. You know, you could have red 3, red 4, red 5, etc., red 6, red 7, red 8, whatever you want to put. You know, that's the way it would work. So that's how the crossing light works. Now what I've done, if you want to run this code for yourself, I have put a serial print statement in here. Now if you're running this for yourself, just uncomment that serial print statement and watch what happens to the fade in and fade out value of the LEDs. It is unbelievable. It is about 10 to 20 times slower than when that is commented out, and that is the impact of having that blocking code. 4.3 milliseconds doesn't sound much to us, but actually it is a huge amount of time when we consider what is actually going on here, because this code that we're using changes every 1 millisecond. So when we do a serial print, it actually delays this code 4.5 times the value of the fade delay that we would normally be using. Hence the reason it makes such a mess. So this is the code for that hand controller, and obviously it updates time, it's sending stuff via ESP now, there's an encoder button, encoder changes, screen presses and stuff. The code, if I'd put all of the functions above the setup as I did in the example that we're using, it would have got crazy, because I'm going to be honest with you, there is miles of code, and this is where these tabs at the top can be very, very useful. Tabs are added on the top right, so it means if you had a particular area where you'd got a number of functions, sometimes you have a function that calls a function, you can keep them all on one little tab, and then I give them names, and it just means that I can go in and I know exactly where the functions are going to be. Just helps you keep your code tidy. But as you can see, this system works exactly the same using that state machine idea. So back to our state machine code. We've now got this situation, you know, when you're writing your code, if you had other inputs, outputs, they could be added down here. You know, you could have more crossing lights, you could have dozens of them on here. If you can get your code written correctly, these functions are literally going to take microseconds to run. They're not going to block each other. They'll all feel like they're all running simultaneously, when in fact all it's doing is swapping between all the different tasks, but only for a fraction of a second in each one. That's basically how a state machine works. Obviously I'm using it for model railways. It could be used for many other things, but I hope if you sort of download the code and take a look, hopefully it will be useful. I hope you remember when you're going through your code, you know, just beware of those serial print statements, because they are going to slow it down. Beware of the dreaded delays. Beware of code that starts to go round in big loops, because again, if you've got endless loops, especially if it's got any kind of delay or serial print, you are going to add ages to your code. So that's the basics of a state machine. I hope it's been helpful, and if it has, please click the like and subscribe. Bye for now. Now, as we look at our code, one of the things I would encourage you to do, you'll notice everything I've done all sits in its own little function. I don't leave all the code in the loop, and this is a really good habit to get into, because it then allows you to think, okay, everything to do with the green light is here, everything to do with the fire flicker is in here, everything to do with buttons. As you get into more complicated code, this has its advantages. It means every time you want to add a new item, you just add a new function. Now obviously that can get quite big. I'm just going to bring in some other code. This is a hand controller I'm working on. I'll just let you see the hand controller in operation. So this is the code for that hand controller, and obviously it updates time, it's sending stuff via ESP now, there's an encoder button, encoder changes, screen presses and stuff. The code, if I'd put all of the functions above the setup as I did in the example that we're using, it would have got crazy, because I'm going to be honest with you, there is miles of code, and this is where these tabs at the top can be very, very useful. Tabs are added on the top right, so it means if you had a particular area where you'd got a number of functions, sometimes you have a function that calls a function, you can keep them all on one little tab, and then I give them names, and it just means that I can go in and I know exactly where the functions are going to be. Just helps you keep your code tidy. But as you can see, this system works exactly the same using that state machine idea. So back to our state machine code. We've now got this situation, you know, when you're writing your code, if you had other inputs, outputs, they could be added down here. You know, you could have more crossing lights, you could have dozens of them on here. If you can get your code written correctly, these functions are literally going to take microseconds to run. They're not going to block each other. They'll all feel like they're all running simultaneously, when in fact all it's doing is swapping between all the different tasks, but only for a fraction of a second in each one. That's basically how a state machine works. Obviously I'm using it for model railways. It could be used for many other things, but I hope if you sort of download the code and take a look, hopefully it will be useful. I hope you remember when you're going through your code, you know, just beware of those serial print statements because they are going to slow it down. Beware of the dreaded delays. Beware of code that starts to go round in big loops, because again, if you've got endless loops, especially if it's got any kind of delay or serial print, you are going to add ages to your code. So that's the basics of a state machine. I hope it's been helpful, and if it has, please click the like and subscribe. Bye for now.